Hello, class. My name is Angel Mack, and today I'll be presenting on climate change in the Southern Ocean and Equatorial Pacific, insights from radiolaria and phytoplankton studies. These tiny ocean organisms, though microscopic, provide crucial insights into past and present climate changes and their implications for future ecosystems. The image here, captured by National Geographic, showcases several types of plankton. This world map from Geology News and Information highlights the five oceans, with the Southern Ocean and Equatorial Pacific circled in red. These regions are vital to the planet's climate system. The Southern Ocean acts as a massive heat sink and carbon dioxide sink, buffering against climate change, while the Equatorial Pacific drives global weather patterns like El Nino, influencing droughts and floods worldwide. However, both regions are undergoing significant changes. The Southern Ocean is rapidly warming, with altered wind patterns affecting ocean currents, while rising temperatures in the equatorial Pacific are impacting ocean productivity. These shifts are reflected in marine plankton, which form the foundation of ocean food webs. As National Geographic explains, they provide the base for the entire marine food web. Let's explore how radiolaria and phytoplankton help us understand these changes. Radiolaria, a type of zooplankton, serve as tiny climate archives. Their fossilized remains in the ocean sediments document past climate conditions. A study by Trubovitz et al. Examined radiolaria in the Southern Ocean and Equatorial Pacific over the past 10 million years. The findings were striking. During periods of coolings, 71% of high latitude radiolaria species went extinct rather than migrating to warmer waters. As the study states, marine plankton species cannot always track preferred habitats on a global scale and are instead acutely vulnerable to extinction during intervals of considerable climate change. This shows how rapid climate shifts can reconstruct your ecosystems. This map from Trubovitz et al. Illustrates the biogeography of radiolaria, highlighting their distribution across different latitudes and depths and how these patterns have shifted over time. Shifting to current trends, a 25-year satellite study by Tamala et al. Reveals significant changes in Southern Ocean phytoplankton blooms. Traditionally, these blooms follow a predictable seasonal cycle, peaking in the spring and summer when sunlight and nutrients are abundant. They are vital for sustaining marine life from krill to whales. The study found that blooms are now shorter and less predictable, with durations in some areas decreasing by 20 days per decade. These changes are linked to warming temperatures, increased ocean stratification, and altered wind patterns. As National Geographic notes, climate change and rising sea temperatures pose serious risks to plankton populations. This graph from Tamala et al. Highlights these regional changes. Red areas indicate regions where blooms are becoming shorter, while blue areas show regions where blooms are lasting longer. In contrast, the equatorial Pacific has maintained stability in radiolaria species richness over the past 10 million years, but the stability doesn't mean immunity to change. This comparison from Trubovitz et al. Shows differing radiolaria trends in the equatorial Pacific and Southern Ocean. While the equatorial Pacific has experienced modest temperature shifts, the Southern Ocean has seen a 35% decline in radiolaria species richness. This contrast underscores the different sensitivities of these regions' climate change. The equatorial Pacific stability may be due to its lower magnitude of temperature change. However, future warming could push its ecosystem beyond their tolerance, leading to cascading effects on biodiversity and global climate patterns like El Nino. So, what does this mean for the future? In the Southern Ocean, shorter phytoplankton blooms and the loss of cold-adapted radiolaria threaten the marine food web. Species like krill, seabirds, and whales rely on predictable blooms for survival. As Tamala et al. Explain, the predominance of shorter blooms is expected to have negative implications for carbon drawdown and trophic supply. This means fewer phytoplankton to absorb CO2, weakening the ocean's role as a carbon sink and reducing food for marine life. Meanwhile, in the equatorial Pacific, radiolaria remains stable for now, but warming could disrupt these ecosystems, affecting global climate patterns. Tamala et al. Figure shows how phytoplankton blooms are becoming increasingly unpredictable, with cascading effects on ecosystems and climate dynamics. In conclusion, this food pyramid from Silence Learning Hub illustrates plankton's central role in marine food webs, highlighting the urgency of protecting these ecosystems. Radiolaria and phytoplankton are not merely tiny ocean drifters. They are critical indicators of climate change. The Southern Ocean is facing significant biodiversity loss and reconstructioning, while the equatorial Pacific remains stable but vulnerable to future warming. Monitoring these trends is essential to understanding how marine ecosystems and the global climate are interconnected. As National Geographic emphasizes, the survival of these tiny plants and animals is essential for healthy marine ecosystems. Thank you for watching.